Bismillahirrahmanirrahim. Assalamu alaikum everyone. Today what we're going to do is finish up with section 16.2, and in reviewing some of the lessons I decided that we would not do 16.3. Instead we'll move on to something a little bit more interesting, which is chapter 18 after this. So this is the last of 16.2 that you would be responsible for, inshallah. So I don't know how far you've gotten with the electric force and your understanding of it, but basically this takes the electric force, this is called the equilibrium problem. The previous one that we did was called the superposition problem. In the equilibrium problem, basically what happens is we know that two charges always have a force between them, right? And if you can figure out the charge on each one of those particles and the distance between them, then Coulomb's law says that you can actually find their electric force. So now what we're going to do is we're going to work a little bit in the backwards direction. Is we're going to say basically where could we put certain charges so that they're in equilibrium, i.e. the electric force that's been exerted on them is neutralized. So the net force is basically zero. Where would we put that exactly? In part one of physics, we actually did this with Newton's laws too, where, for instance, we would say if you have a tree, right? If you have a tree and you're trying to make the tree stand upright, so and you were to be holding that tree up with certain wires, then where would you angle those wires so that the tree would be in equilibrium? So the same exact idea is addressed in this lesson as well. So let's go ahead and get started. The question says that you have three charges and they lie on the x-axis. So what I've got here is a diagram that is in the book as well, but here's your x-axis, and I just wanted to explain this to you very quickly because I know the equilibrium problem has kind of been tough for students to understand in the past. It says that one of the positive charges, Q1, so it's the one all the way at the right, is 15 microcoulombs, is at 2 meters on the x-axis. So if this Q2 is at 0, then by that relativity, Q1 is going to be 2 meters away from that. So Q2 is at the origin, they mention again. So Q2 is 6 microcoulombs, and it's at the origin. And it says at what point on the x-axis must you put a negative charge so that the resultant force on it is 0, meaning the force that is pulling the charge towards the right, which we can call F sub 3 comma 1, meaning the force exerted on 3 by 1, is equal and opposite to the force that's exerted on 3 by 2. So if you were looking at this as an equation, you would have said F sub 3 comma 1 minus F sub 3 comma 2 is going to equal a net force of 0. And this is really where the problem starts, because what we're really implying is then in that case, in equilibrium, the two forces are going to equal out to one another like this. All right? So let's go ahead and start with something. But one thing I will tell you is basically it's a bit of a math problem, really. We're saying, well, if the whole distance is 2, let's call the distance from charge 2 to charge 3 as d. Let's call it d. And then whatever distance is remaining, we'll call that 2 minus that d. And that distance happens to be where charge 1 is going to be sitting. So I just really quickly want to detail this example for you to clear all doubt about it. So at the top, I'm going to write down F sub 3 comma 1 is equal to F sub 3 comma 2. And then we're going to write down that Coulomb's constant multiplied by the charge on 3 multiplied by the charge on 1, all of that divided by the distance between 3 and 1 squared is equal to Coulomb's constant, the charge on 3 times the charge on 2 divided by the distance between 3 and 2 as well, squared. Now, we're just going to be picking out the values that have been given to us. But before we do that, if you just kind of look at it algebraically, notice how the Coulomb's constant can actually cross off on both sides. And the charge on 3 is irrelevant because it actually cancels out on both sides. So it's interesting. Even though we're trying to find the equilibrium point for 3, we don't even need to know the charge of 3, meaning it could have been any charge that we wanted, and it would have worked out for us. So the next thing that we'll do is we'll kind of simplify this a little bit. So we know that this is q sub 1, and the distance between 3 and 1, the distance between 3 and 1 is 2 minus d. Again, the idea was the entire thing is 2, and this piece is d, so the distance between 3 and 1 would be 2 minus that d, whatever that distance remains. So I'm going to go ahead and write that down as 2 minus d, but notice how Coulomb's law says they have to square the distance, so you square that distance right there. Then for the other piece, it's q sub 2 over d squared, meaning the distance between 3 and 2, and the distance between 3 and 2 once again is simply d, so you square that. All right, so here goes the little bit of algebra behind this equation. Basically, the first thing that we do is we cross multiply. All right, we cross multiply like this. And so you end up with q1 multiplied by d squared, and it's equal to q2 multiplied by 2 minus d squared. Remember that we already know what q1 and q2 are. We're just trying to figure out what d is going to be. Now, for some of you, you have a very good handle with algebra, so you know how to deal with a situation like this. But I just want to help you out in case you don't know what to do. So the first step that we basically take is we tell ourselves, look, we need to get rid of that square from both sides. So what we do is we square root both sides. Now when you square root both sides, here's what happens. Basically, the d squared, when you take its square root, you simply end up with a d, right? So you simply end up with d. But the square root of q1, that makes it looks really weird, but basically you're just left over with the square root of that number. On the right side, the same exact logic applies. The square root of 2 minus d squared is simply 2 minus d. But the square root of the thing that it was being multiplied to, which is q2, is just going to kind of hang around in there. So you have square root of q2. Now the next thing that we do is we basically use the distributive property. And in the distributive property, we multiply the 2 and the d to the square root of q2. So here's what we have now. We end up with d square root of q1 is equal to 2 times the square root of q2 minus d square root of q2. The next step that we do is we move, because notice how there's a d on this side and there's a d on this side. So what we'll do is we'll move this expression over to the left side. And because that way we'll have grouped the d's. So now we'll have d square root q1 plus, because when the minus comes over to the other side it becomes a plus, d square root q2, and it's equal to 2 square root q2, like this. All right, and we're just about done with this. Now this is a step called factorization. And in factorization, what you do is you factorize what's in common in both of the terms, and you'll notice that what's repeated in both terms is the d. So what we'll do is we'll factorize out the d, all right? So when we factorize out the d, this is pretty much the end of this question. You have square root of q1 plus the square root of q2, and it's equal to 2 times the square root of q2. So to solve for d, what you basically need to realize is you got to divide on both sides by the square root of q1 plus the square root of q2, like this over here. So square root of q1 plus the square root of q2. And that's going to cross off everything on the left side. And on the right side, you basically have an expression that'll give you the distance between those two that should be there between the particles. And so like this, we can actually solve this, and I'm quite confident that you know how to plug into a calculator. But let me just review these steps with you really quickly. So in the equilibrium problem, it really starts off with you setting up a equation that involves equaling out the forces. Then in step number 2, you basically cross multiply. In step number 3, what you do is you take square roots. In step number 4, you use the distributive property. In step number 5, you factorize out the d, and you help yourself by solving. So it's like a 6 or 7 step problem depending on how you look at it, and I just wanted to kind of go through that with you, and that's one of the reasons why I split the lesson up into 2 parts. Um, there is very little more about the lesson that remains. Basically, here's the small little conversation piece. Is we talked about this in the beginning, and we talk about it again now. Is basically the electric field force. Electric force is a field force because contact is not required. Okay, so you can. Contact is not required. You don't need for contact to happen for this force to exist. And one of the people who discovered this, and that's why we gave the charges his name, is Coulomb set up what's called a torsion balance. And so I'll link a video to this torsion balance that will help you understand the idea. And so for this set, now that I'm done with it, you want to basically take a moment and you want to copy down these problem sets answers, right? And I've got 3 questions that I will have you guys complete and turn in along with, I believe, the section review. Thank you so much for listening, and Assalamu alaikum.